Today in the role of crystals, we will focus on actually the defects in crystals. Okay. So, even though crystals have a very regular structure, but in nature hardly such regular structures will be followed. So, hence the defects that we will come across in a crystal structure at various length scales etc., we will focus on that today. So, thus we will first give an introduction on the crystal defects, we will then talk about point defects, line defects, plane defects and finally the volume defects. So, the first point is that when the crystal is forming, if you know let us discuss that, we have earlier also discussed about it. So, let us look back at this, that from a liquid stage we are gradually, through a gradual process of cooling, we are getting the crystal structure, right. If we want to make the cooling process to be very fast, then what we are going to get is the glassy amorphous structure. So, hence a very controlled, uniform, gradual cooling is the must in terms of developing a crystal structure. Now, when you are from this molten state, you are actually taking a material to the solid phase, the first thing that would happen is that there will be the sight of new thermodynamic phases, which we will call as the nucleations. So, the nucleations, as has been shown here, that various nuclei will start and these nuclei will grow to form the crystals. And these crystals will start to grow up to a point when they will meet each other. When they will meet each other, then we are going to get actually the grain structure. Okay. So, basically grains are crystals, but they are crystals grown up to such an extent that each crystal structure is getting in touch with another crystal structure. That is when we will say that now from the basic crystal structures, the grains have been formed in the system. So, this is how the solidification process occurs. Now, in this solidification process, not everything goes perfect. So, there will be lot of scopes of things getting disturbed, and many of these disturbances will result on what we say that the crystal defects. So, any deviation that we will observe in an ordered arrangement of constituent particles in a crystal, we call them to be defect or imperfections. Now, why it is important? Because the properties of the material are actually influenced by the presence of these imperfections. That is why it is important for us. Mechanical properties, for example, of pure metal, that changes significantly when metals are actually alloyed. Now, alloys are actually intentional creation of disturbances or defects in a crystal structure to improve the material properties or mechanical properties of a metal. People have understood it initially intuitively, you can say, when you have talked about the from the copper age to bronze age. Okay, people have understood that something happens when copper gets mixed with other impurities. Similarly, when we have talked about from iron age to steel age, okay, if you remember those various types of steels, the early steels in southern part of India, for example. Okay, so, all these people have realized that carbon as an impurity plays an important role in the crystal structure of iron to actually improve the properties of iron drastically. So, the copper, for example, when you take pure copper, its yield strength is 117 megapascal, but you mix this copper in a ratio of 70% copper with 30% zinc, you get actually brass, and you see the brass's modulus of elasticity yield strength is 200 megapascal. So, thus it is important for us to know about how many types of imperfections are possible in any regular ordered crystal structure, what are the roles of each one of them in terms of the material properties of the systems. Now, to do that, that means we have to clearly classify the types of defects. So, the major types that we can say is that the point defects, which are actually 0 dimensional, we will put more emphasis on that in this lecture. Also there are other defects like line defects, which is like dislocations, that is 1 dimensional in nature, plane defects which are like 2 dimensional, in which grain boundaries will come, twin boundaries will come, and finally volume defects which are 3 dimensional, in which pores, cracks, etc. will come. Now, in the point defect itself, there are about 5 to 6 categories of it. For example, the vacancy defect, interstitial defect, substitutional defect, Frenkel defect and Schottky defect. So, we will talk about all these types of defects in today's lecture. So, let us first start with the point defect. Now, this is associated with the atomic sites happening inside a crystal structure, and it may not be very regular in nature, it may be just irregular in the sense that in a regular lattice, but not, it may not be periodic in nature. At different points you may suddenly see that one atom is missing from the regular lattice site. If this happens, then this is called the vacancy. So, and this is something that is very real in this system. It is impossible to create a material which will be free from the vacancy defect. Now, here is an example that you have a regular structure, suddenly one atom is missing here. Okay, so, there is a vacancy here. Now, presence of this vacancy, naturally what happens, it increases the disorderliness or the entropy in the crystal, that is one thing. What are the other things that is happening? It actually decreases the density of the substance, because there is nothing there, there are voids type of a thing there in the atomic structure. So, it is going to decrease the density. The concentration of vacancy, if increases when there is an increase in temperature. Okay, so, at a higher temperature it is found that vacancies are more. Why? Because atoms are more mobile basically, and in fact something more happens at that high temperature, that decreasing activation energy. Okay, so, in fact the number of vacancies you can actually compare it using Arrhenius law, that the number of vacancy is actually varying with the activation energy and the temperature. Okay. So, as the activation energy is reducing, as the temperature is increasing, you are actually going to get more number of vacancies in the system. Now, there is another form that can happen when the vacancy is there and suddenly an impurity, because you will never see a very pure material, suddenly an impurity goes and says, okay, there is a vacancy, let me push myself inside it. So, that is called interstitial defect. Now, if the atoms from the same group goes and pushes itself, then it is actually self interstitial defect. Sometimes atoms of different kinds or impurities like a foreign atom can occupy it, then then it is not self interstitial, but it is just in interstitial defect. In fact, if you can see that a vacancy and a self interstitial defect may be actually kind of an inverse way of two phenomena, because suppose where there is a vacancy, there is supposed to be an atom there, but this atom, due to the say increase of temperature, due to the decrease of the activation energy, this atom has jumped out of its location and went and pushed itself in one such place. That way it is stressing the region here and it is creating a kind of a pore here. So, that is what is happening, that vacancy is happening at one place, at the same time self interstitial phenomena is happening at another place, and both of them may become actually coupled with each other. There are some examples like carbon forms an interstitial solid solution when it is added to iron, and what will happen if you look at it, that the atomic radius of carbon is only 0.071 nanometer, which is much less than that for iron. So, it is for iron it is 0.124 nanometer. So, that means there are plenty of space in between the iron atoms, where this 0.071 nanometer carbon atom can go and push itself inside. The moment this happens, it actually generates a stress on all the neighboring iron atoms, and that actually significantly changes the material properties of the system. Now, sometimes there will be substitutional defect also. Substitution happens when the atom that is substituting is nearly of the same size of the original atom. So, they will not disturb the crystal lattice, and they will, and also the atom which is coming, the foreign atom itself should have a crystal structure which is very much similar like the atom in which it is going to go and sit itself in. So, this happens many a times between copper and nickel, because if you look at it, copper's atomic radius is 0.128 nanometer and nickel's atomic radius is 0.125 nanometer, and both of them actually creates a FCC solid solution. So, it is very easy for copper to substitute nickel. Okay. So, that is how the substitutional defect can get formed in the system. Now, there are two more varieties of these actually point defects. These are specifically these things arise for ionic structures, okay, where crystal structure which is mostly having ionic bonds. Let us say salts or ceramics, you would see this more. The first of them is called actually the Frenkel defect. It is a combination of vacancy and interstitial defect. The only thing is that this is happening when an atom or an ion leaves its regular site and occupies an interstitial site. Okay. So, then it is known as Frenkel defect. Cations are generally smaller in size and they get displaced to interstitial voids. Now, in such a case, because one ion is leaving its position and it is going to another position, so generally this happens continuously, and as a result no change in the density occurs. And this is very peculiar, that this is generally absorbed in ionic compounds which has actually low coordination numbers, okay, something like calcium fluoride. So, that is where you will see the Frenkel effect. There is another point defect which is known as Schottky defect, and here it is always it has to be a paired set of cation and anion. Okay, that emphasis on pair is important, because then there will be an electrical neutrality in the crystal. Now, in this case the density of the solid decreases because it has to happen in pairs. So, there will be lot of actually vacancies. So, the density of the solid decreases, and it is found in ionic compounds with generally high coordination numbers. And in order to maintain the electrical neutrality, as I told you earlier, the number of missing cation and anion are to be equal. So, something like sodium chloride, potassium fluoride, etc. In both Fresnel and Schottky, no change in electrical neutrality of the crystal is observed. So, thus we have kind of gone through various types of point defects. Okay. We have talked about the vacancy defects, we have talked about the what you call interstitial defects, and then we have talked about substitutional type of defects, and then Frenkel and Schottky defect. Now, let us look at the linear counterpart. Okay. So, from the point, now we are going to line defects or dislocations. Now, there are, even though we call it line defects, it need not be like a straight line, it can be in a curve. Okay. So, it can be in terms of a edge dislocation, it can be in terms of a screw dislocation or rotational dislocations, etc. Now, what is this dislocation? In this case, it is actually not a phenomena with one single atom, but rather while building up the crystal structure, for some reason, because of various disturbances, one layer of crystal structure may not get completed, and by nature it is just like a whimsy of nature that one extra half plane of atoms is left in between. Now, this extra half plane that is there, it will actually distort all the nearby planes, and then actually this dislocation is coming into picture. Now, this dislocation line in this particular case, as you can see, is perpendicular to the plane of the page itself. Okay. So, this is the edge dislocation that we are talking about. the direction and magnitude of this dislocation is given by a vector which is known as Berger vector. So, how do we get this dislocation? Okay, so, to do that you have to move around the dislocation line in a clockwise manner, making equal steps in each direction. So, the vector goes from finish to start position, the Berger vector, okay. And what you will see is that when you will reach the dislocation point, you will see that the edge dislocation is generally perpendicular to the Berger's vector, and this dislocation creates normal stress and strain in the crystal naturally, and also it affects the other material properties like strength and plastic formation, flow, etc. So, you need not have a planar dislocation always, okay. You can have a dislocation which is like a screw dislocation, okay, which actually is something like a shear that is happening in the system. So, if there is something like a shear, once again you can move around the dislocation line clockwise as has been shown here, and from finish to start with the help of Berger vector, and this Berger vector what you will see is actually parallel to the dislocation in this case. In the last case that it was perpendicular to the dislocation, and here it is parallel to the dislocation. So, a screw dislocation lies parallel to its Berger's vector, and it moves in a direction perpendicular to the Berger's vector. So, that is when we have screw dislocations. Now, how do we avoid dislocations? First of all, why do we need to avoid dislocation? Well, in most of the cases it is a defect which is something which is not negligible, because it is a long scale of a defect. It is not just one single atom is missing, but rather entire half plane is missing. So, what the way it can affect is, one, definitely in terms of the strength of the system, and there are other things also possible, that is in terms of the nature of the system at a high temperature, for example, the creep behavior of the system, and also it affects the damping of the system. Now, one way to avoid dislocation is that dislocation is happening when a crystal structures, there are many crystal structures, and suddenly one half plane is missing in a polycrystal structure. If you use a single crystal structure, generally to do that you actually control the environment to a very good degree, you can avoid the dislocation. For example, turbine blade making this is done, but it is very expensive, okay. That is why it is not usually done. The other way to do is actually work hardening. Now, because dislocations are happening inside the grain structure, okay, so what you can do is that through work hardening you can move all dislocations to the grain boundaries. So, when the dislocation will become essentially a part of the grain boundary, then we can say that this strengthening to plastic deformation has happened, and there is a work hardening that has taken place in the system. This is done in a regular manner, particularly for developing very high strength surfaces. Let us say wherever there is a point contact and there is a danger of wear and abrasion, the work hardening is required, and there this can work in a much better way. The other way to actually avoid dislocation is actually you introduce impurity into the atom, so that it goes into that dislocation space, it fills up the space, okay, and thus it makes the whole system to be stronger. So, these are various ways of actually dislocations that you can control. Now, that is about the edge dislocations. If you expand that, what you are going to get is called surface or planar defects. So, the planar defects are something that what you will see in general is in the grain boundaries itself. The boundaries that separate the two grains of crystals having different crystallographic orientation, Okay, this is where you will see this grain boundaries, which is a two-dimensional defect. Now, why it is, how it is going to affect the material property? Because the atoms which are near this grain boundary, suppose here we have a grain boundary, right. So, the atoms which are near the grain boundary, they are slightly distorted, we can say, and have higher energy than those within the grains. Now, in general, a grain boundary is assumed to contain 5 degrees of freedom. These 5 degrees of freedom, out of that there are 3 degrees of freedom which are related to the orientation of one grain with respect to the other, and there are 2 degrees of freedom to specify the orientation of the grain boundary itself. So, thus there are 5 different degrees of freedom by which the grains can move against each other along the grain boundary, and hence can significantly control the material properties of a system. Now, how would it actually affect? One is that at temperatures which is actually greater than 0.5 Tm, less Tm is the melting point temperature, then the grain boundaries will actually start to flow. But when it is less than 0.5 Tm, this will work like an obstacle to the dislocation. It will not, the grain boundaries will not allow the dislocation to propagate very easily. On the other hand, at a higher temperature, they will tend to weaken a material. Why? Because the grain boundary sliding may occur. Each grain boundary may slide with each other. So, that may result to the plastic flow and opening up of voids, etc., along the boundaries. In general, what we think is that single crystal structures are good. Otherwise, if you have to go for a polycrystal structure, then you should go for a fine grain materials which are actually stronger than coarse grained ones. Why? Because they have actually more grain boundaries per unit volume. So, grain boundaries are actually making the structure stronger. Now, how do we first of all know that what is the grain boundary? There is a ASTM E112 standard of ASTM, which says that this average number of grains per square inch at a magnification of 100x is related to the grain size by this particular relationship. So, which is a very useful relationship, because in the next slide I will show you how to use this relationship. So, if you look at it, that there is this these examples. The first one is that you have to determine the ASTM grain size number of a metal specimen if 45 grains per square inch are measured at a magnification of 100x. So, the ASTM standard method is that this n is equals to 2 to the power n minus 1, where n is the grains per square inch and small n is the grain size number. Now, if you take a logarithm, you get a simplified relationship like this. So, in this particular case, we have said that the capital N is actually 45, that is the 45 grains per square inch, and the the denominator is log of 2, of course, that is fine with us, and then there is a plus 1 which came from this relationship. So, once I know that how many grains are there per square inch, I can actually find out what is the number n that we can find it out. Similarly, in yet another problem, suppose we use this equation where we have the percentage of grains and we have grains per square inch. The n small n is something like 6.5 and the capital M is 85. So, if we carry out this exercise, we will see that Nm will come out to be something like 62.6 grains per square inch. As I told you that finer grain structure, that is more number of grains per square inch, is actually good for us if you cannot go for a single crystal structure. Hence, this determination is very useful for us. The second important point here is that there is this slip system. I told you already about slip plane and slip directions. They together form something which is called the slip system. Okay. And in the slip system, the slip plane is generally taken as the closest packed plane in the system, and slip direction is generally the direction on the slip plane with the highest linear density. Okay. So, why are we talking about highest linear density? We have also addressed this problem in the last class, where we have said that if there is a high linear density, then it is always easy for many things to happen fast using those atoms as the pivotal lines. Okay. I have given you an analogy of ragging pulling a carpet or a rug below, if you have certain number of kind of bearings or balls, then it is much easier for you to pull. Okay. So, here also the same way, if you have more number of slip systems, then actually if you have higher linear density, that would mean, so then you are going to get actually the slip directions along that direction itself. FCC structure, for example, it has 4-1-1 family and of slip planes, and as such this planes contains 3 of the family which are of 1-0-0 with caret directions, and there are altogether 3 into 4. So, that means about 12 slip systems. Similarly, in BCC structure, there are actually 6 1-1-0 planes with 2 of the caret 1-1-0 direction in each, and that gives about 12, 6 into 2, that is about 12 slip planes. So, what do we conclude from this? That FCC and BCC materials, both of them has large number of slip systems, and that is why they are considered to be ductile material. Now, HCP on the other hand, okay, hexagonal closed pack systems, they have only 3 slip systems, and that is why they are quite brittle in nature. So, the slip system plays a very important role to actually define the nature of the particular material. Now, what we will see is that what is the a very special case of twining that you will see in terms of the grain structure, when particularly you will see that this is happening with a symmetry line like this. Okay. So, with a very definitive way that this kind of symmetric lines are going to actually, for example, this particular case, this is the symmetric line. This is going to move the atoms in a flip-flop conditions. This flip-flop condition, I have given you earlier an example of shape memory alloy. I will come back to it at a later stage. Now, this can be in the form of mechanical twins, which occurs generally in BCC and HCP crystal structure, or you will see the annealing twin, in which the deformation is due to the annealing itself. Okay. So, annealing is actually heating the material followed by slow cooling to remove the internal stresses and toughen it, and this occurs mostly with FCC crystal structure. So, that is about the twining. Now, twining plays a very important role because those crystal structures which can twine more, like HCP structure can actually twine more, and out of the BCC and FCC, both of them are fine, but BCC actually twines more, but those which can actually twine, they can be used for phase transformation. So, FCC BCC structures will not usually twine because the slip is more energetically favorable, and this twining generally happens at low temperature and at high rates of shear loading like shock loading. It there are few such slip systems which are present in the system, and there is a small amount of deformation. Okay, if you consider this in comparison with the slip. In fact, memory effects is one of the most prominent example of this kind of twining, but we will talk about it at a later stage. Finally, we will talk about volume and bulk defects. Okay. So, we have talked about point, line, surface, now then the volume. This happens mostly during the processing and fabrication, like the pores come. Okay. So, that is a defect, or cracks is a defect, foreign inclusions and other phases, these are all defects. They are always undesirable, first thing, bulk defects, and they decrease the mechanical strength and promote the fracture. So, that is what is the kind of a flip side of a bulk defect. Now, let us try to draw a kind of a summary of what we have discussed today. Okay. So, we have talked about various kinds of defects. First of all, vacancy, substitutional, interstitial, if you remember. There are the properties which are affected are the solid state diffusion, mechanical creep, conductivities, then the magnetic coercivity, dielectric constant and optical transparency. The way you can remove these kind of point defects are age old, the traditional process is through the annealing. We call it hit, beat and treat system. Other than that, the other ways are like semiconductor diodes and transistors, okay, and solute hardening of alloys, where you can apply strong permanent magnets development, capacitors, coloring of glasses and plastics. You can actually apply this presence of defect by converting it what you call the bone in the cars. The edge dislocation, okay, or similar type of other the screw dislocations, etc., they are actually plastic deformation and they have applications in terms of strain hardening. The grain boundaries, okay, so they affect the dislocation movement, electrical resistance. The more the grain boundary you have, more resistance, magnetic coercivity, optical transparencies, etc. And the proper applications are in terms of mechanical hardening or strong permanent magnets. Then of course, there is the stacking faults, which is generally it affects the mechanical strength and the electrical resistance itself. So, this is where we will put an end, and in the next lecture we will learn metals like ferrous alloys, their properties and classification. Thank you.